Asteroid 2025 QD8 swept past Earth on September 3, 2025 at 28,000 miles per hour, and that speed reveals something surprising about our cosmic neighborhood. This jet-sized space rock, measuring 71 feet long, cruised safely by at 135,500 miles away, roughly half the distance to the Moon. What makes this encounter fascinating isn't the asteroid itself, but what its speed tells us about the cosmic shooting gallery we call home. 28,000 miles per hour sounds incredibly fast, but it's actually slow by asteroid standards. That translates to about 12.5 kilometers per second, placing this space rock on the gentler end of the cosmic speed spectrum. To understand why this matters, we need to explore what happens when worlds collide. Earth gets bombarded constantly. Every single day, our planet absorbs roughly 100 tons of space material. Though most burns up harmlessly as meteoric dust, the bigger chunks that survive the plunge through our atmosphere are moving fast. Really fast. Any object hitting Earth must travel at least 25,054 miles per hour. That's our planet's escape velocity, the minimum speed needed to break free from Earth's gravitational grip. Anything arriving from space has to move at least this fast, or it never would have escaped wherever it came from. Think of it as a cosmic speed limit in reverse. Nothing can go slower when it reaches our doorstep. Most asteroids scream through space much faster than this minimum. The average impact velocity for asteroids hitting Earth reaches around 38,000 miles per hour, with many clocking 60,000 miles per hour or more. The fastest asteroid to buzz Earth within the Moon's orbit this year blazed past at 63,400 miles per hour. At the other extreme, the slowest close approach crawled by at a leisurely 7,000 miles per hour. So 2025 QD8's 28,000 mile per hour approach was relatively sedate, but don't mistake slower for harmless. Speed represents only part of the destruction equation. The energy released when an asteroid impacts something scales with the square of its velocity. Doubling the speed doesn't just double the energy, it quadruples it. A 71-foot asteroid like 2025 QD8, if it actually struck Earth at 28,000 miles per hour, would still pack enough punch to level a city. Consider what unfolded over Chelyabinsk, Russia, in 2013. An asteroid just slightly smaller than 2025 QD8, about 66 feet across, plowed into our atmosphere at 42,690 miles per hour. It never even reached the ground. Instead, it exploded about 19 miles up, creating a flash brighter than the sun and releasing energy equivalent to 30 atomic bombs. The shockwave shattered windows across 6 cities, damaged 7,200 buildings, and sent 1,500 people to hospitals. The explosion echoed 600 miles away. That Chelyabinsk meteor traveled about 50% faster than our September visitor. But here's the terrifying part. Nobody saw it coming. The asteroid approached from the sun's direction, hidden in its glare until it started burning through our atmosphere. This detection gap remains one of the most unsettling aspects of planetary defense. We're improving at spotting these cosmic bullets, though. NASA's Planetary Defense Coordination Office currently tracks over 1.3 million known asteroids through its Sentry monitoring system, with more than 30,000 classified as near-Earth objects. This year alone, astronomers have logged 189 asteroids that passed closer to Earth than the Moon. Most were small, harmless chunks of rock and metal. The fact that we're detecting them at all represents a revolution in astronomical surveillance that's emerged just in recent decades. The challenge extends beyond finding these asteroids. Predicting what they'll do if they hit us matters enormously. Size determines everything. Objects smaller than about 10 meters typically disintegrate harmlessly in the atmosphere, creating spectacular meteor shows, but no damage. Between 10 and 50 meters, you get Chelyabinsk-style events, dangerous but localized. Above 50 meters, you're looking at Tunguska-level destruction. Scientists use the Torino scale to categorize impact risks, with ratings from 0 to 10 based on collision probability and energy. The Tunguska event of 1908 flattened 830 square miles of Siberian forest when an asteroid roughly 100 feet across exploded with the force of 1,000 atomic bombs. If that same asteroid had struck New York City instead of remote Siberian wilderness, it would have killed millions. The asteroid responsible was probably traveling around 60,000 miles per hour when it arrived. Interestingly, we commemorate this event every June 30th as International Asteroid Day, designated by the United Nations to raise awareness about asteroid threats. Even Tunguska pales next to what larger asteroids can accomplish. Objects over 1,000 feet across cause regional devastation. Above a kilometer, you're looking at global climate effects. Anything over 6 miles across, like the asteroid that killed the dinosaurs 66 million years ago, can end civilizations. The good news is we've found about 95% of the really big ones, the civilization enders, and none are currently aimed at Earth. The bad news is we've only spotted about half of the 140-meter class asteroids, the ones that could destroy entire metropolitan areas. NASA's upcoming NEO Surveyor mission, scheduled for launch in the late 2000s, aims to close this detection gap by discovering potentially hazardous asteroids in infrared light. This is where asteroid speed becomes critically important for planetary defense. We now have proof that we can change an asteroid's trajectory. Last year, NASA's DART mission slammed into asteroid Dimorphos at 14,000 miles per hour, successfully altering its orbit using kinetic impactor technology. The impact shortened Dimorphos's orbital period by over 33 minutes, far exceeding the mission's success criteria. But DART also revealed something unexpected. The collision shook loose 37 boulders from Dimorphos, each measuring 3 to 22 feet across. These chunks now drift through space, and if they ever reached Earth, they'd hit at the same speed the original asteroid was traveling. It's an unintended consequence that highlights how much we still don't understand about asteroid deflection. The key insight is that successful deflection requires early warning. According to congressional testimony, NASA needs at least 5 years to mount an asteroid deflection mission, 5 years to design, build, launch, and navigate a spacecraft to intercept a cosmic bullet traveling tens of thousands of miles per hour across millions of miles of space. This brings us back to 2025 QD8 and what its 28,000 mile per hour flyby really means. Astronomers discovered, tracked, and predicted that asteroid with enough precision that NASA knew exactly when and where it would pass Earth. The fact that it moved only 28,000 miles per hour gave astronomers more time to study its trajectory and confirm it posed no threat. We're about to get an unprecedented opportunity to study asteroid behavior up close. In April 2029, asteroid Apophis, a 1,100-foot space mountain, will pass just 19,600 miles above Earth's surface. That's closer than some of our satellites. Apophis will be moving at about 25,000 miles per hour during its approach, and it will be visible to 2 billion people across Africa and Europe. It's likely the closest approach of such a large asteroid in recorded human history. Remarkably, Apophis once reached level 4 on the Torino scale, the highest rating ever assigned to any asteroid threat. Scientists are calling Apophis a natural experiment that maybe happens once in human history. NASA has redirected OSIRIS-APEX, formerly OSIRIS-REx, to study it during the flyby, while ESA is developing the Ramses mission as a complementary observer, hoping to learn how near misses with Earth affect asteroid structure and rotation through the Yarkovsky effect. The 28,000 mile per hour speed of 2025 QD8 tells a larger story about our solar system. We live in a dynamic, violent cosmic environment where city-sized chunks of rock and metal regularly cross Earth's orbit at speeds that would vaporize anything we've ever built. The fact that this particular asteroid cruised on the slower end of the speed spectrum doesn't make it less remarkable. It makes it a perfect example of the constant, invisible threat streaming through the space around our planet every single day. Every asteroid encounter teaches us something new about the physics of these cosmic encounters and brings us one step closer to defending ourselves when the next Chelyabinsk-sized asteroid comes screaming out of the sun's glare at 40,000 miles per hour. Because it's not a matter of if, it's a matter of when.